My talk is about a multi-criteria decision support system to explore the feasibility of actions triggered in a warehouse by operational earthquake forecasting. We have used a technique of order preference similarity to the ideal solution and incorporated it with a kind of cost-benefit analysis to come up with a framework for decision makers. Firstly, we have created a matrix of the impacts based on an action would have, and then normalize and weight them based on the importance of each category. The final output is the closeness value, which is called C value, the similarity to the best possible solution. This could be used in future applications to determine which OEF mitigation actions are recommended. As an example, boxes falling in a warehouse has been seen in many past earthquakes. As an example, you can see FEMA 2012. We have assumed 4 different actions, including no action, moving boxes to the floor, securing boxes to shelves, and moving boxes to storage. We have used the Patras city as a testbed in Greece, and the seismic data are gathered from ESH M13 project. And we have multiplied the seismic data, the hazard curves from seismic data by a set of probability gain values to come up with the heightened seismicity situations. We also have made several other assumptions to make this problem simple. In summary, you can see the proposed hybrid model of incorporation of TOPSIS and cost-benefit analysis. The top matrix is the consequence matrix for example, A1 action and different criteria such as direct cost, downtime, and casualties. For example, for the direct cost, the consequence is the expected A1 action direct and reconditioning costs plus expected direct cost from estimated shaking that is not eliminated with mitigation action A1. We can translate these data to the decision matrix, and furthermore, we can come up with optimal action. If you follow the blue route, you can see that we can come up with the cost of a specific action and also mitigated loss by that action. And if we divide them and multiply it with the probability of exceedance to hazard, we can come up with a benefit to cost ratio, R value. And this is called cost-benefit analysis. The final decision will be made based on an action which is recommended by the TOPSIS, as well as it should be financially justifiable based on the cost-benefit analysis. As you see here, the results are presented in 2 figures. The left figure shows the results of the TOPSIS algorithm. The vertical axis is the C value, shows the closeness distance to the optimal solution, versus the x-axis, which is PGA threshold for different earthquake thresholds. As you see, the no action case would be justifiable in higher PGA thresholds, and also moving boxes to storage is always recommended by the TOPSIS with far distance from other actions. The benefit to cost ratio is shown in the right graph, and as you see, the moving boxes to storage is not the best financially justifiable action, but still it is financially justifiable, at least in lower PGA thresholds. A combination of TOPSIS and cost-benefit analysis for the case of probability gain equal to 10 is shown here. The top row is the TOPSIS only results, which shows that the moving boxes to storage is always recommended by the TOPSIS algorithm. And the other rows below are used to represent the cost-benefit analysis results for different ranges of R values. If you see for lower PGA thresholds up to 0.2 G, the R value is more than 5, which means that it is highly cost beneficial. And from 0.25 G to 0.35 G, it is between 2.5 and 5, which is clearly cost beneficial. And the similar trend goes for moderately and marginally cost beneficial. And if the R value is less than 1, it is not cost beneficial here when the PGA threshold is more than 0.6 G. This is based on our recent work about the cost benefit analysis, which is published in Natural Hazard Journal. The results for different probability gains are presented in this slide. The top figure is for probability gain equal to 1, and the bottom right figure is for the probability gain equal to 100. As you see, the trends are the same, and also in the case of probability gain equal to 1, the moving boxes to storage is recommended for even low PGA thresholds less than 0.15, which means that in the normal situation, even the OEF actions might be recommended. If we use different weighting schemes when using the TOPSIS algorithm, we can use the end user's preferences to build up the framework. For example, for the left figure, we have put emphasis on the direct cost by allocating a higher weightings for that. For example, here we allocate 0.5 weighting, means 50% weighting for the direct cost and 25% weighting for the other criteria. And as you can see, the no action case would be recommended when the PGA threshold is more than 0.2 G. And still, the moving boxes to storage is the superior action, but the distance between different actions are less. It is the case for downtime as well, when the downtime weight is 50%. But in the case of injuries, if we put 50% weight for the injuries and 20% weight for the direct cost and downtime, you can see that the no action is never recommended. To come up with the conclusions, I would say that OEF mitigation actions are viable even in the normal hazard situation. And the results show that the OEF mitigation actions are beneficial if damage is caused by low shaking levels and when the actions are cheap enough and can mitigate a significant portion of the underlying risk. The cost-benefit analysis doesn't always confirm the TOPSIS results. Therefore, we have made a hybrid model of the both algorithms. The final decision should be adapted based on the end user's preferences, and the approach can be tailored to other situations which are not shown here, but we have submitted a paper to the International Journal of Disaster Risk Reduction, which is under review, and hopefully we'll see soon this paper in this journal. Thank you for your attention.